Hello, everyone. Thank you for joining us today for this super spreader seminar series under the guide of Professor Jack Blair, Arnie, and Professor Huai-Ping Zhu. And today is our fourth seminar. And first of all, we want to make the land acknowledgement. So maybe I just skip this one. So because there will time we repeat for this. And this series is for all the highly qualified personnel to present their research and promote their ideas and share the research experience. And our next one will be in 3 weeks. So this is for the December 8th. So that's our next one. And for today's talk, our speaker is Yi Tan. She is a PhD candidate in the Department for Mathematics and Statistics at York University. And she's also a member of LAMPS and CCDM and OMNI. Her research interests are stochastic differential equations and their applications in biology. She has been working on modeling of infectious disease and zoonotic disease. She participated and contributed to several projects on the COVID-19 and monkeypox in collaboration of Ph.D, the City of Toronto. And today, she will talk about the stochasticity in adherence to non-pharmaceutical interventions and the booster doses and the mitigation of COVID-19. So over to Yi. Let me stop share.
Yes, let me share my screen now. Thanks, Pei, for the introduction. And also, I would like to thank OMNI for giving me this opportunity to share our work. Yeah, as you can see on the screen, today I'm gonna talk about the stochasticity in adherence to non-pharmaceutical interventions and booster doses and the mitigation of COVID-19. And first of all, I would like to thank our collaborators. Firstly, our LAMPS CCDM team leader, Professor Zhu, for his constant support and expert opinion on the project. Also, Dr. Pei Yuan for her constant contribution and efforts. Also, Professor Ian Mollis from York University, Professor Jen Heffernan from York University, Professor James Watermore from University of New Brunswick, and also Professor Sanyi Tang from Shanxi Normal University. My presentation today is structured as follows. First, I would like to talk about the introduction, and then I will illustrate our stochastic differential equation model with demographic and environmental stochasticity for COVID-19. And our main focus is on our simulation results, which is about effects of stochasticity on the COVID-19 outbreak dynamics. Lastly, I will give the conclusion. First, for the current outbreak scenario across the world, we can see there have been 632 million confirmed cases, including nearly 6.6 million total deaths. And also this figure shows the number of daily cases in 6 WHO regions. we can see Europe and America reported the highest number of cases. And also on the right hand, I show the comparison of cases this week with previous week. We can see there is an increasing trend in the number of cases. The number of new weekly cases increased by 2% during this week compared with previous week. And I would like to see there could be some underestimation for the cases, because as we know, many people with COVID-19 may not included in those numbers, either because they are asymptomatic infected or they are not officially counted for some reason. And here, I list the variants of concerns. We know virus mutate over time, and some mutations can affect virus characteristic in a meaningful way, leading to variants of concerns. Those following 5 variants are being monitored across Canada. We know alpha variants is 50% more transmissible than the original virus. And also Delta variants is 60 more transmissible than the alpha VOC. Not only the transmission probability and ability will change due to the mutation, but also the vaccine effectiveness, testing strategy, and also control measures could be affected by those VOCs. And then I will give a brief introduction about the current circulating variants, Omicron. We know it spreads more easily than earlier VOCs. And according to the data, we can see Omicron can cause reinfection. People who have recovered from COVID-19 may be infected again. And also the symptoms for Omicron are similar to previous variants. Besides that, the death rate is low for the Omicron. I think one of the reasons is because due to the help of vaccine, so less people died. And the continuous emergence of VOC is one of the reasons for the changing situation of the transmission of COVID-19. So here is the current situation in Canada. As of yesterday, we can see there are total nearly 4.4 million confirmed cases in Canada. And we can see there are more than 8 waves in Canada. And on the right, I present the number of cases previous week. We can see Ontario and Quebec reported the highest number of cases, with more than 5,000 people infected per week. And there are some mathematical modeling, especially the deterministic approach has been widely applied to design the control measures for COVID-19. Here I list some work from our labs group, and also there are thousands of great work on this topic. But I would like to see the transmission nature of COVID-19 being probabilistic, that's stochastic. So it is necessary to incorporate stochasticity when we model the transmission of COVID-19. Firstly, I would like to introduce the demographic stochasticity, we know in the ODE approach, the model assumes individual changes their infectious state by a same rate. However, it is more nature to consider that individual changes their infectious status by chance. Those refers to the demographic stochasticity. Here, I give a simple example for the meaning of demographic stochasticity. If we consider people change their epidemiological status from exposed class to the infected class, in the ODE model, we can calculate the number of infected people within a small delta t, which is E divided by tau times the time step delta t. However, in stochastic model, we can consider this process is a stochastic process. So we can give them some distribution. For example, we can assume it satisfies normal distribution, gamma distribution, or other distribution, and or general distribution. We consider we can give all the probability of number of recruitment of infected cases. Here as I show here, the probability of the number of recruitment of I equals to E divided by tau times delta T. And those stochasticity causes fluctuations in the population size of each state, but also it could causes a systematic deviation from ODE behavior. As I list some reference here, we know a large outbreak can be visible in the ODE model when the basic reproduction number is larger than 1, but it is not the case for the SDE model with demographic stochasticity. And others also prove that the stochastic effects due to demographic variation could dramatically alter the time course of the infection. So in our work, we will incorporate the demographic stochasticity. Besides the demographic stochasticity, there's another environmental stochasticity. Actually, there are many variations due to external conditions like the rainfall or temperature, and also human behavior change across time. Those kind of change could lead to time varying parameter values like the transmission rate, recovery rate, or death rate. So this lead to the environmental stochasticity. So what's the relationship between the previous demographic stochasticity and the environmental stochasticity? We can understand their relationship in such a way. Like I mentioned before, we can consider the transition process from exposed class to infected class satisfies distribution. For example, the normal distribution. We know there are 2 parameters defines the normal distribution, the average value mu, and also the standard deviation sigma. So the demographic stochasticity is reflected in the normal distribution, and the environmental stochasticity is reflected in the parameter mu or sigma. If mu or sigma also satisfy a stochastic process, I mean, it changes stochastically with time, this could be referred to the environmental stochasticity. In conclusion, not only the process itself is a stochastic, but also the parameter satisfy a stochastic process. So, and here I listed the importance of environmental stochasticity. I would like to mention the last reference by NEPA. In their work, they found that the stochastic oscillations in transmission rate results in reduced probability of outbreak occurrence, but severe outbreak with increased total numbers of infections, deaths, and peak number of infections. So it is important to incorporate environmental stochasticity to see how the external change or behavior change affect the transmission of COVID-19. Here in our work, we consider two kinds of stochasticity, two kinds of environmental stochasticity. The first one is the stochasticity in adherence to NPIs. We know NPIs have played a critical role in reducing the transmission of COVID-19. However, it has been nearly 3 years after the COVID-19 pandemic. So individuals' behavior or attitude towards NPIs change over time. For example, people decide several times per day how closely they follow the mask wearing recommendations. Also, in the beginning of this year, there are some regulations on indoor activities. Some people obey with restrictions, but some are not. They may have parties or they go outside to enjoy the meetings with others. So people's attitude and behavior towards NPIs really change with time. And these asynchronous changes in behavior among the population result in different transmission probability or context over time. Those kind of change can be reflected in the random transmission rate. For the work of transmission of COVID, little attention has been paid on the stochasticity in the transmission rate. And although there are available works use the basic diffusion process to describe the stochasticity in the transmission rate, the full effect of stochastic transmission rate on the prevalence of disease is unclear. How does those stochastic change in behavior result in different patterns of COVID-19 still remain unclear. And then I will also incorporate the stochasticity in vaccine boosters because we know people's attitude towards the vaccine also change with time. There is a Canadian surveys show the people's willingness towards vaccine shift over time. And also in UK, vaccine hesitancy has shown an oscillating descent since the beginning of vaccine rollout. Also, a report from New Zealand shows the changing intentions to vaccine. Those kind of uncertainty in vaccination attitude could result in a random number of vaccinated people each day and influence the number of susceptible individuals. So we will incorporate this kind of stochasticity. Here, I will give the overview. Although the NPIs and the booster doses are encouraged to mitigate the epidemic, the uncertainty and the stochasticity in individuals' behavior towards NPIs and booster dose increase. So here in our objective, in our work, our objective is to analyze the effects of two kinds of environmental stochasticity. As I mentioned before, one is in the NPI adherence, and another is in booster dose acceptance on the outbreak dynamics of COVID-19. After that, we want to investigate the implications for public health sectors given the presence of stochasticity. To do that, we adapted previous work from our labs group. We incorporated the testing strategy for Omicron in Ontario. Here, I2 represents the reported cases, and I1 are those who are not reported. And here, compartment V represents people receive the booster doses, and lambda is the daily vaccination rate, and epsilon is the efficacy of vaccine. Based on this ODE structure, firstly, we incorporate the demographic stochasticity. We used the method popularized by Linda Allen. We can construct the continuous time Markov chain, and we know within a small time delta t, only one event of the following 9 compartment, 9 changes could occur. So we can calculate the mean and the variance of this stochastic process, and then we approximate to a stochastic differential equation model, as I list here. Those model has a vector of 9 independent one-dimensional Wiener process, illustrating the demographic stochasticity in the transmission process. And the next step is to incorporate the environmental stochasticity. Here we use the linear function of Gaussian white noise to model the stochastic transmission rate. And here beta bar represents the mean value of the transmission rate, and the sigma beta is the volatility for the transmission rate. Those sigma beta could reflect the stochasticity in the transmission rate. And then we use the BK process to reflect the stochasticity in the vaccination process. Here, BK process is a well-known mean reverting process. And in the model of BK process, the R represents the speed of change to the mean value, and the sigma also represents the volatility for the vaccination rate. If we incorporate those two equations to the previous demographic stochasticity model, we will have our final version of the model with demographic stochasticity and environmental stochasticity. Then based on this work, firstly, we calibrate our model. The data of COVID-19 outbreak with Omicron variant in Toronto from December 31, 2021 to March 8, 2022 is used for model calibration. And we used the approximate Bayesian computational method to estimate parameters. Here, as I show here, the simulation is good, the estimation is good, and all the circles represents the data, and the curve is the result, which are the average of 1,000 runs. and the areas gives a 95 confidence interval of predictions. And based on this, I stated the parameters, we see the effects of stochasticity. Firstly, we consider there is a change of the volatility for transmission rate. We varied the value from 0 to 2 for the volatility. And we gave the results of reported cases and unreported cases under two different mean value transmission rate. We can see there is a plateau and the increase in the number of cases. If we mark this minimal value of cases as a turning point, we can see the stochasticity in the transmission rate has a significant effect on the outbreak when the volatility is larger than the turning point. And then we conduct the scenario analysis. We consider two scenarios. One, there is a stepwise reopening strategy in place, and also we consider there is a stepwise closing strategy. Firstly, for the reopening strategy, we consider the mean of transmission rate varies in stages. And also, we plotted the results of ODE model, the model with demographic stochasticity and the model with environmental and demographic stochasticity. We see that compared with, and also the inner plot shows the cumulative number and the curve represents the daily number of infected cases. We see that compared with the outcomes of ODE model, the presence of demographic stochasticity worsens the outbreak with more infections, especially when it comes to the total reopening stage. We can see there is a high peak value of daily reported cases and a short peak time. And we also noticed that the situation became worsened when further incorporating environmental stochasticity. We can see the model with those environmental stochasticity reported the highest number of cases. This implies that it will more people will be infected due to the environmental stochasticity. So for the public health sectors, we could suggest that it will be beneficial to alleviate variations in transmission rate by reducing the oscillations in behavior. And also for the stepwise closing strategy, we can see the demographic stochasticity could worsen the outbreak with more infections.